Imagine the universe as a cosmic billiard hall, but instead of balls, we have photons and electrons. One of the most fascinating games here is the collision between a photon, a tiny packet of light, and an electron. This is the Compton effect discovered by Arthur Holly Compton in the 1920s. Before this, light was mostly seen as a wave, but the Compton effect showed that light can act like a particle too. When a high-energy photon, like an X-ray, hits an electron, it bounces off, losing some energy and emerging with a longer wavelength. This simple collision changed physics forever, proving that light isn't just a wave, it's also a particle. The Compton effect helped launch the quantum revolution, revealing the dual nature of light. In this video, we'll break down what happens in this collision, the equation that describes it, and why it matters. By the end, you'll see how this effect reshaped our understanding of reality. Let's dive into the heart of quantum mechanics. Let's set the stage. A high-energy photon, like an X-ray, is speeding toward a stationary electron. The photon's energy is given by E equals sign Hn, and its momentum by P equals sign Hl, where H is Planck's constant. High frequency means high energy and short wavelength. The electron, for our purposes, is at rest. Its initial momentum is zero. In classical theory, light would just make the electron wiggle and radiate waves of the same frequency. But in the quantum world, something different happens. The photon is about to collide with the electron, not just pass by or get absorbed. This is the moment before the quantum crash. The outcome will reveal the particle-like nature of light. The classical wave theory can't explain what's about to happen. The quantum script is about to unfold. Let's see what happens next. The photon strikes the electron like a cue ball hitting another ball. The photon isn't absorbed. It scatters off at an angle, now called the scattering angle, theta. After the collision, the photon has less energy and a longer wavelength, lambda prime. This change in wavelength is the signature of the Compton effect. The electron, meanwhile, recoils, gaining energy and momentum from the photon. The total energy and momentum are conserved, but now split between the two. Classical wave theory can't explain this precise change in wavelength. The fact that the photon's wavelength increases by a specific amount is proof of a particle-like collision. Light, in this case, acts as a discrete packet of energy, a photon. This tiny collision shook the foundations of physics. Let's see how we describe it mathematically. The Compton effect is captured by a simple formula, the Compton shift equation. It tells us how much the photon's wavelength changes after scattering. The equation deal equals sign lambda, lambda equals sign h mech x1 cos theta. Here, h is Planck's constant, m is the electron's mass, c is the speed of light, and theta is the scattering angle. The term h or mech is called the Compton wavelength of the electron, about 2.43 picometers. If the photon scatters straight ahead, theta equals sign 0, there's no change in wavelength. At 90 degrees, the shift equals the Compton wavelength. The key insight: the shift depends only on the angle, not the photon's initial energy. This was a bold prediction, ready for experimental testing. The math perfectly describes the quantum collision. Now, let's see how Compton proved it in the lab. The experiment would change physics forever. How did Compton derive his equation? By using the laws of conservation of energy and momentum. Before the collision, total energy is the photon's energy plus the electron's rest energy. After, it's the energy of the scattered photon plus the recoiling electron's energy. Both energy and momentum must be conserved. No losses, just redistribution. Momentum is a vector, so it's conserved in all directions. Compton wrote equations for both energy and momentum, treating the photon as a particle. With some algebra, he solved for the change in wavelength, dl the result, the Compton shift formula. This wasn't just a guess, it was a direct consequence of the universe's most fundamental laws. Now, it was time to test it. A theory needs proof. In 1923, Compton set up an experiment to test his prediction. He used X-rays as his photon source and a block of graphite as the target. Graphite's loosely bound electrons made it ideal for the experiment. Compton aimed X-rays of known wavelength at the graphite and measured the scattered X-rays at different angles. His detector, a spectrometer, measured the new wavelengths. The results were clear. At each angle, there was a second peak at a longer wavelength, matching his formula exactly. The shift in wavelength increased with the scattering angle, just as predicted. This was direct evidence of the Compton effect. The experiment proved that X-rays scatter from electrons as if they were particles. Compton's work confirmed the quantum theory of light. The Compton effect was now a fact, not just a theory. The quantum revolution had its proof. The Compton effect was more than a scientific victory. It was a revolution. It proved wave-particle duality. Light can act as both a wave and a particle. Classical effects like diffraction show light as a wave, but the Compton effect shows its particle side. This duality is a core idea of quantum mechanics. The billiard ball collision of photon and electron is undeniable proof of photons as real particles. The discovery reinforced the idea that energy comes in discrete packets, quanta. The Compton effect moved physics from the smooth world of classical mechanics to the strange, granular world of quantum reality. It laid the foundation for modern physics, from lasers to computers. In summary, an X-ray photon hits an electron, scatters with a longer wavelength, and the electron recoils. The Compton shift equation, derived from conservation laws, describes it perfectly. Compton's experiment confirmed it, proving light's particle nature. The Compton effect changed our view of reality and opened the door to the quantum age.